Okay, I think we are ready to go. So, hello everybody. Good morning, good afternoon, or good evening. I see we have participants from all over the world. So, welcome to today's webcast. My name is Amir. I'm with Anybody Technology, and I'm the host of today. And we will have presenter Julien Groud today. He will talk about musculoskeletal forces in the human body during Tokyo's daily life of commuting. Before I go and introduce Julian, today's outline is I'm going to present very short who and what is anybody, and then I will give the mic to Julian. And then at the end we will have a short summary, and then we will answer questions live for you. So before I start, there's going to be a recording of this webcast, and we're going to put that on our YouTube channel within the next days, where you can then listen again if you missed something to this webcast. We will also give handouts of this presentation, so we will probably send a PDF around in a couple of days. So if you're not getting everything right now, there's a chance to read it afterwards in the webcast, in this PDF of this webcast. Also, you should see a little box called questions behind the orange arrow of this GoToWebinar window. And if you have any questions, please feel free to type them in there whenever you want. So even while I'm talking or later on while Julian is talking, I have a couple of colleagues with me here that will answer those questions either immediately, or I or Julian will answer something at the end. Or if they are maybe too complex, we can either answer them later on by email, or we can get back to you and talk to you right afterwards. So about anybody, so who is anybody actually? There's Anybody Technology. This is also the company what I'm working for. We are based in Aalborg in Denmark. We have also an office in Boston or in Salem in the United States. Anybody Technology develops the Anybody modeling system, so that's the software, and we provide licenses, training, and support of this software, and we also provide consultancy projects around musculoskeletal simulations. On the other hand, there are research groups, so Anybody research groups. One of them is based in Denmark at the Aalborg University, which is headed by Professor Rasmussen. This research group is headed by Professor Rasmussen, and he's doing a lot of research projects in the area of biomechanics, ergonomics, sport, and also automotive. There's another research group at the Colorado School of Mines in Colorado, headed by Professor Tony Petrella, and he's doing a lot of projects using Anybody in the field of biomechanics, orthopedics, and sports. And third, there's another group in Germany at the OTH Regensburg, headed by Professor Sebastian Dehndorfer, and he's also doing a lot of biomechanics, orthopedics, and gait projects, research projects. I also want to mention that there are some Anybody resellers all over the world, especially in Asia, and especially mention I want to hear our reseller of Japan. This is a company called Terabyte, and today's speaker, Julian, is working for Terabyte, and he's doing some projects, some interesting research projects and consultancy project for Terabyte, and he's presenting some of his models today to us in a couple of minutes. So before we go to Julian, a little bit more, so what is Anybody? So there are actually two products. So one is the Anybody modeling system, which we usually abbreviate with AMS. So this is the actual software, so the tool of it. On the other hand, we have the Anybody managed model repository, which is the library of the applications, but also of the body models. So this is basically where all the body segments and the information on the body is, but then also where you will have a library of applications. And if you have the anybody modeling systems or the software, you will always get the anybody managed model repository with this software. So musculoskeletal simulation in this case works that you use a motion or activity as input. You have then your body model, which consists of bones, joints, muscles, and ligaments. And then as output, you will have muscle forces, activity, power, and also joint forces and moments. So this is basically means that we use the principle of inverse dynamics. So that means that we use motion as input. This can be either from motion capture systems like Bicon, Qualisys, also Xsense, or maybe also Kinect, or you can use joint angles as input. So you can define the joint angle over time for certain joints like the knee, the ankle, or the hip, and then you can create a motion with those individual inputs. Then on the middle animation you see then would be basically an output. So you would get muscle forces, and here they're just presented as lines, so blue and red lines on the tibia. So these are all the muscles that are acting on the tibia, and you see here the line or the direction how they are acting, and then also a rough magnitude. So you would have the muscle activities and muscle forces in there. On top of that, of course, also the joint reaction forces. On the right side on the slide, you see the full body model with some details, like we start on the bottom here. So we have the detailed foot model, the knee model, hip. We have the lumbar spine, which is very detailed, and then the shoulder. And altogether, we have a full body model, which is the most sophisticated musculoskeletal model that you can find at the moment. So typical applications are, if you start here in the top and go clockwise, so it would be product design optimization. So you can optimize products related to the human body. So how, if you want to design, for example, a wheelchair, how would the design be to have the lowest loads in the shoulder? It can also be used for ergonomic analysis and documentation, very often in the area of automotive. Then also in surgical planning, so how has a implant in the spine, what loads does it have to carry for certain activities? You can also use those loads, those physiological loads, and create special load cases for finite element analysis, for example with ANSYS or Abacus. And then finally we also have a gate application called AnyGate, where you can process gate trials very easily and very quick. So this will result in a standard workflow. So you have an animation activity, and then you can analyze that in the anybody modeling system to calculate muscle activities, forces, and joint forces moments. You can also create, in a more advanced workflow, patient or subject-specific models. So if you have CT scans, MRI scans, for example, from mimics, you can hook that up with anybody, and then instead of using our standard bones, you can use the morphology of certain subjects that you have, and then you can export everything into finite element models. And more recently, we have also added the opportunity, if you have assemblies in SolidWorks, you can create with the interface SolidWorks to anybody, you can import this whole environment into the anybody modeling system very easy with only a couple of clicks, and then you have everything in the anybody modeling system, like for example a bicycle, or here it's an elliptical trainer. And there's also the option to hook the anybody modeling system up with other higher programming languages like Python or some other optimization softwares. So that's my part now for anybody. So I hope you know now who is anybody, or who are the anybodies, and what is anybody. The speaker of today's presentation is Julian. He was at the IPSA in Paris, got an engineering degree there in aeronautic and aerospace systems. He moved on then later to work as an engineer and a consultant in Simpo, and first in Paris, then he went to the US, so he was in San Francisco for a while and finally in Tokyo. And since a little more than 1 year, he changed and is in the engineering department now of Terabyte. And I mentioned before, Terabyte is the distributor or the reseller of anybody in Japan. And there he has done a couple of interesting models in the past. And he will give a presentation now about musculoskeletal forces in the human body during Tokyo's daily life of commuting. So, Julian, if you're ready to go.
Yep.
Okay, I mute myself.
Okay. Could you make me presenter? Yeah, thank you. Okay, so now everybody should see my screen. So, good morning or good afternoon, everybody. My name is Julian. I'm working at Terabyte, and today I'm going to present musculoskeletal forces in the human body during Tokyo's daily life of commuting. So basically, I'm going to talk about 3 modes of transportation, so commuting transportation, motorbike, bicycle, and train. And actually, the train case is more specific to Tokyo's daily life. But first, a brief introduction of Terabyte company. This is the company I'm working with. So we distribute software, software solutions for structure, fluid dynamics,
Julian,
and electromagnetic.
can you switch to full screen, maybe?
Oh yeah, please. Sorry. So we distribute solutions for structure, fluid dynamics, and electromagnetic softwares, and we provide, indeed, we distribute anybody modeling system in Japan, and we provide the technical support in Japanese language. So this is just a brief introduction of Terabyte company. So today's summary, the first case is I'm going to talk about the effects of motorbike acceleration on the human body. Then I'm going to, so it's an ongoing study, just to introduce the possibilities of anybody software with bicycling, commuting. So some different configurations, just a brief introduction. It's not finished yet. We are still working on the project. And lastly, the main topic of this presentation is the comfort of the passengers when they are commuting by train in standing position. So the effects of motorbike acceleration on the human body. So we have a sports motorbike like this one, and we would like to know for a given acceleration of the motorbike, what will be the muscle activation of the whole body. And basically, can the person handle such acceleration force? So some conditions that we consider for our study. The motorbike will accelerate from 0 to 100 kilometers an hour in 2.5 seconds. So it's a pretty brutal, pretty strong acceleration. And the last condition, the biker must hold the riding posture. The person must do whatever it takes with his muscles to make sure to hold the same posture with this acceleration force. So the way to proceed, first, anybody software comes with some templates. One of them is just the human body, standing person. So this is already defined in anybody. You have bones, muscles, joints, and ligaments. And this is the posture we would like to mimic. Basically the riding, sports, motorbike riding posture. So there is a kind of interface dedicated to this where you can set the anthropometric dimensions of your postures. So basically elbow, shoulders, ankles, angles, etc. So little by little you set your angles, and then you get to get this kind of posture that resemble a lot to the one we wanted. So we have the human model and the posture. Now we need the motorbike. So basically you can input the STL geometry of the motorbike if you have it. So I assume that most of the motorbike companies have the geometries of their motorbikes. So you can input it in anybody. If you do not have it, you can still create some what we call segments. It's actually rigid bodies that will mimic the steps, handles, and the seat. So this is what I did. I created it here in blue, the handles, steps, and seat, and then I will create joint condition. So connection condition with the hands, the foot, and the bottom of the human model. So with I've created a spherical and cylindrical joint condition with 3 degrees of freedom for the spherical joint condition. And then we have to model the acceleration of the motorbike. So the way to proceed is, so with anybody, you can, anybody will calculate for you the body center of mass location. So this is the ball you can see here, and then you can apply a force on it. So we will apply a force which is created by the acceleration. So in the next slide, I will display the results. So here you can see the motorbike speed from 0 to 100 kilometers an hour in 2.5 seconds, varying like in an exponential way. Here you can see the maximum muscle activity. As you can see, we start from a pretty low value. There is a kind of balancing while the motorbike is accelerating, and then the body needs more activation to hold the posture. And also you can see the reaction on the saddle. More interestingly, you can see each muscle buckling, and also the color is changing. When it turns to yellow or green, the muscle activation gets more intense. So we can easily notice that to hold the posture, the human model will use a lot his arms, the spine muscles, and the abs. And at the maximum, the human model will use about 40% of his muscle capabilities. So this is just a quick analysis here. I would like to talk about further possibilities. If you are a motorbike company, you probably have some more detailed acceleration time information, so you can input the profile of it, so from an Excel file or a time function as I did. So you can input more accurate data here. You can indeed change the motorbike dimension and shape, and of course it will have some incidence on the human posture and on the results. If you do not want to input the whole motorbike, you can still input the seats, handle, and steps in STL geometry. It's also interesting that you can scale the biker. Not only male are riding motorbikes, so what if a female will try to accelerate with such abrupt acceleration? So you can also analyze if the human model will succeed doing this or not. Also, you can scale the height and weight and body fat percentage. So what if a tall, fat person tried to ride such acceleration? It will have some incidence on the muscle force indeed. You can also consider other comfort criteria. You can study charge on the spine, reaction forces on shoulders, joint reaction forces on shoulders, etc. And by the way, while I'm presenting, you should see this kind of window on GoToWebinar interface. You can type in your questions while I'm presenting, and staff will answer your questions. We'll try to answer your questions while I'm presenting. The second case is bicycling. So it's an ongoing study. This is just to introduce the possibilities of anybody with the bicycle, commuting in bicycle. So it's not about high performance cycling, just we want to focus on comfort for people that are commuting in bicycles. So some people are actually in Japan, a lot of people are commuting to their train station in bicycle. So what we can do is to study different cycling activities, different cycling positions of the rider. What's a good position, a comfortable position to ride a bicycle, and different bicycle types. And the steps, so for different cycling activities, slow pedaling, stop and go, getting on and off the bike. Some people that are working by bicycle, like postmen, for example, they could, like every day, get on and off 100 times, more than 100 times. So it could be interesting to find the right way to do this kind of movement. You can scale the rider just like the motorbike. So what if a male or what if a female, height and weight, body percentage. Different bike dimension and rider posture. So upright, like the animation you can see here, or more sporty, as this animation is showing. Another interesting thing about Anybody software, anybody can handle buckle movement. So from a computation point of view, it's not something easy to handle because there are no initial conditions. It's just an ongoing a buckling movement. So it's not something that all the competitors can handle. So I think it's interesting to mention. And for the studies of the bicycle, you can study comfort criteria. There is a big, huge freedom in what you can do when you see comfort or position, etc. So overall muscle activation, loads on the spine, the hip, knees, etc. Okay, so the main topic of today's presentation is about comfort of passengers commuting in standing position in a train. So I'm living myself in Tokyo, in Japan. You should see a picture of this city. Just a quick presentation of Tokyo. It's a very big city. I think you should see about 10% of the city in this picture. So it's really huge. There are 35 million of people in Tokyo. And more interestingly, 20 million of them commute every day by train, twice a day. I think it's the world's largest commuting amount of people by train. And so it needs a very efficient train system to make sure all the people can go to their work. And also, I'm mentioning that Tokyo still have the world's highest urban agglomeration GDP. It means that this is very efficient. So people arrive at work on time. They can work properly. So it works well. And no matter how numerous they are, people can arrive on time. And it's a lot of people commuting by train. But at what cost? If you see this picture, people are packed, basically. So sometimes it's chaotic, and sometimes it's well organized. It depends on the mood of the people. And standing posture is by far the most frequent one. So myself, I'm almost never sit in the train in the morning or at night. It's too crowded. And depending on the posture you choose, and actually you don't choose your posture, it's more the design of the train or even the crowd. It's so crowded that you don't even choose your posture. And so it may hurt. So you have a standing posture. Some people will push you to some directions. It may really hurt some people. So the goal of this presentation is what's a good posture, standing posture, to travel safely by train or to be the most comfortable. This is the topic of this study. So the conditions for this study, I'm going to create a kind of ideal environment. The train will accelerate of about 4 kilometers an hour per second. It's about 2.5 miles per hour a second. Up to 90 kilometers an hour, which used to be a cruise speed of the train. And the train is going to accelerate until the speed and then brake to to the next station. The human model is 1.7 meters tall and weighing 75 kilograms. And the model must activate his muscle to hold a standing position. So the human model won't fall down on the ground. He will do everything possible to stay upright and while the train is accelerating and braking. And lastly, the passenger won't use the handrest. So there is so few handrests that most of the time you cannot handle it. So that's our conditions for this study. So how do we model the train acceleration? Just like the motorbike case, there is a function in Anybody called AnyKincon that will display and calculate and display the location of the body center of mass. And then we are allowed to apply a force on this body center of mass. This force can be obtained by the second law of motion. The force equals the mass by acceleration. So the mass, this is the body, the human model, so it's 65 kilograms. And the acceleration is the one of the train, about 4 kilometers an hour per second. As you can see here, there's a picture of the modelization, so the train ground, the body model, and the ball here for the body center of mass, and the train direction. About the acceleration, so we're going to use this value, and basically to reach the cruise speed, the train will take about the train is going to take 22.5 seconds to reach the cruise speed, and then take just the same time to brake, so obviously the braking time to the next station. If we use this, if we use this value, it will give a train speed like this one, so from 0 to 90 kilometers an hour, and then decrease to 0. But I do not think it happens like this. For comfort issues, we can assume that the variation of speed is not abrupt or smooth. So basically, I used a cosinus function to create the time function of the speed to create something smoother like this one. So the train speed will increase smoothly, reach the cruise speed, and then will brake smoothly, assuming it happens like this. And once we have this time function of the speed, we differentiate it to get the time function of the acceleration. And so we can easily calculate, so we use this time function of acceleration here, and we have a time function of the acceleration force in the model. So to find the right posture, we are going to introduce a parametric study. I'm going to study two parameters. And the thing I want to mention is that you have the freedom to study the parameters you want. So it's not a limitation of anybody. This is my own choice. So what I've decided is to study, so the first parameter is the train direction. Is it better to be face the train direction vector, or to be transverse to it? And in between, I'm going to study every 5 degrees the passenger direction regarding the train direction, from 0 to 90 degrees. And the second parameter is the passenger feet distance. So I'm going to make vary. So is it better to have our feet close or about 1 meter of distance, like this one, assuming it makes sense? So in total, we're going to study 190 different postures. And then what's about comfort? What can we call comfort in standing posture? So from my own feeling, when commuting by train, I was thinking it would be interesting to study 2 criteria. The first one is the muscle activity. I want to use my muscle as less as possible. This is the most, this is the priority criteria. The second one is the reactions at ankles. I noticed that sometimes my ankles hurts while commuting, so I was thinking that having reactions at ankles as low as possible could be interesting, could be one of the comfort criteria. So in the next two slides, I'm going to show the results for each posture for those two criteria. So this one, here in this 3D graph, you can see all the postures, so 190 postures, results for the max muscle activity. So I'm not talking about ankles yet, just what is the activity of muscles to hold each posture. Something interesting is that when the passenger is facing the train direction and when his feet are closer, the activity gets higher. So I'm going to ignore those high values. And actually the best position to, so from a muscle activity point of view, is to have a 60-degree of angle regarding the train direction and 1 meter, so the maximum of a feet distance. And with such posture, the model is going to use about 20% of his muscle activity, so of his capabilities. To give you a comparison element, the normal standing posture is about 13%. So it's pretty close. The worst position is when the person is facing the train direction and when his feet are pretty close, 20 centimeters. Then it goes up to 53%. So more interestingly, for the next criteria results, I won't take into account those values. I noticed that there is a range, a domain like the one you can see in green, where values are pretty similar, between 20 and 22% of maximum muscle activity. So I'm going to take all those values only and see for each posture what is the reaction at ankles. This is the next slide. So this is this graph. Something interesting. So this graph is showing the anteroposterior and mediolateral reaction forces at ankles. If you do not know what this means, there is a schema here showing the reaction vectors I want to study. So I am summing those two magnitudes, and I want those vectors to be as low as possible to get some comfort. So the first thing to notice is that the posture that was the most comfortable from a muscle point of view is actually one of the worst if we take into account the ankle reactions. It's pretty high. So what is the lowest value from an ankle point of view? It should be 90 degree and 0.4 meters. So the model is going to be, the human is going to be transferred to a train direction and having a pretty reasonable distance between his feet. And this seems to be, so again, all those values already have a very low level of muscle activity. And what you have in this range, in this domain here, are all of the low values. So it doesn't matter if you do not have this exact posture, everything close will get you some more comfort. So for the next slide, I am showing this posture. So we can see here the train speed. This is an animation. So from 0 accelerating to the cruise speed and then decelerating to the next station. At the same time, you can see the max muscle activity variation. You can see each ankle reaction vector. And here you can see the train acceleration vector, the acceleration force. So here it's braking. So right now it's braking and then accelerating. So another thing to mention about this slide is that we get this result as the best posture, as the most comfortable posture. And from what I have seen while commuting is that many people actually take this posture naturally. So they get into the train, they make a U-turn on themselves, and then push backward the crowd, so the people to back the crowd. And I really have seen some situations where all the people had this same posture. And it's interesting because I would assume that most of the people are comfortable, and you can even put some more people in the train. Because as you know, Tokyo is a crowded city, it needs some optimization. Again, further possibilities. I assume that train companies have more detailed acceleration time profiles, so one can input some more accurate data of so in Excel file or a time function as the one I did. You can consider the train inside environment by STL geometry file of the seats, holding bars, handle. You can make a simulation of someone sitting in the train. There is a model already created for this that comes with Anybody software. You can scale the passenger. This is very important because not only very healthy people are commuting, there are also old ladies, fat and tall guy. So it has some incidence on the muscle maximum forces. And also some people are weak at their knee, so it might be interesting to understand this. So you can scale to male and female, height and weight, body fat percentage. You can consider overall more comfort criteria. So again, knee reaction for all people, for example. You can study a specific muscle and its activity, and you can study other postures. So what if a people is moving in the train while accelerating, etc. So that's pretty much it for my presentation, and I will first thank you very much and pass it on to Amir for the end of this presentation. Thank you very much.
Okay, thank you, Julian. Thank you very much for this interesting presentation. I think you gave a very nice overview of the musculoskeletal loads during different transport possibilities in commuting. Yeah, I think it was very nice to see how you can analyze bicycle, motorbike, and also train, subway environment. And I think it's always so interesting to use these models for optimizing, for example, a bike or a motorbike, and then also the environment for a train or subway. So we got a lot of questions actually. Before we go to the questions, a couple more notes. So feel free to ask us if you have any questions right now. There's of course also the chance to talk to us in person. So we are, from Anybody, we are very often at conferences. There's, for example, in Shanghai next week, the Congress of Orthopedic Advanced Techniques. There's also in Tokyo, that's highlighted here because it's together with Terabyte. So we have an Anybody forum. It's also next week with Professor John Rasmussen is going to be there. There's the chance to meet us in Aalborg, so right next to our headquarters in June at the ICNLR. Or of course, I think many of you who are in the field or in the area of biomechanics will go to Boston in July to the World Congress of Biomechanics. So I will be there as well. So if you're interested in meeting and talking about certain things, feel free to contact us either before by email or just show up there at we have a booth in Boston, so you can talk to us. On the other hand, if you want to learn more about musculoskeletal simulations, we have courses. So actually there was one just last week in Aalborg here in Denmark, but there's going to be another one in August in Golden, Colorado, which is hosted by Professor Petrella, and it's going to be from the 4th to the 8th of August in Golden, so close to Denver. And there's going to be another one in September in Regensburg in Germany. Please feel free to go to our homepage, anybodytech.com. You can sign up for the courses on our homepage where you find the link there. The easiest way is always to find us online, so either on our homepage here, I mentioned it before, anybodytech.com. You will find a long list of events and dates where we are. You will also find a list of publications, so what other researchers or companies have done in the past using the Anybody modeling system. You can find the list of publications there. Then there's another homepage from the Anybody community, which is called anyscript.org, with a wiki of typical questions, technical questions, and there's also a forum where you can post questions. And there's a YouTube channel with videos, help, demos, tips and tricks, and also a list of webcasts that we have recorded over the last years. You see, you found all webcasts on our YouTube channel there. Then if you want to contact Terabyte themselves, so here's the homepage, terabyte.co.jp. You can find contact there. You get also maintenance or support, technical support in Japanese or in English from Terabyte if you are in Japan.